Good evening, everyone. So, welcome to the week tutorial session on the course Introduction to Robotics. And this is the week 11. So, we will be discussing the questions based on the week 11th lecture, which is taught in NPTEL portal. And also, we will discuss some of the theoretical concepts related to this week. So, the first thing which is taught in this week was the velocity motion model. So, before that, we'll understand some of the terminology regarding with robots while it is navigating. So like a robot initial pose, whenever a robot is navigating, let's suppose this is the map axis, or this is the local or global map axis. This is X, Y, and the out of the plane is the Z axis. So, with respect to the map, let's suppose a robot is navigating. Let's suppose this is our robot and the direction is in this. And the origin of the robot also have a axis. So let's suppose this point is the axis of the robot and this is the heading and the out of the plane is the Z axis. So whenever we say that the initial pose of robot, this means the initial pose means the position of the robot with respect to the map, either the global map or local map. So this is the 0, 0 of the map. So this will have some coordinates according to the map axis. This is the red axis is the map axis. Let's suppose this is like x is equal to 5 and y is equal to minus 1. So the current position of robot is 5, comma minus 1 with respect to the map. So whenever we denote initial pose is the most important thing for the navigation of robot in autonomous mode. So initial pose, let's suppose, is at the time instant t minus 1 that is given as x, y, and theta. So it can be in three dimension also x, y, z, and having three rotational orientation that is roll pitch yaw. But here we are taking x, y, and the heading of the robot with respect to the map frame. And also a control UT can be applied like a action a robot can apply is the UT. So that is the control action. This UT can have either the velocity or the rotation. So here you can see the initial position of a robot is given as xt minus 1 as xy and theta. Theta is the heading of the robot and xy is the position with respect to the global or local map. When we say global map, this means like the GPS coordinate you can take. If we say local map, then the map created using perception sensor like LiDAR, camera or radar or some other sensor as well. And now if the robot is at the position xy theta, it will apply some control action that is the mm, velocity and the rotation. So the velocity is given as v and rotation is given as w. So w is rotational velocity and v is the translational velocity. Like here you can assume v is the translational velocity and w is the rotational velocity. So after this, what happens when a robot applies the control action ut at xt minus 1? Robot will move and reach to the next point. So this is at t minus 1. Let's suppose robot moved and rotated little here. So this is the position of robot at t after applying the control action. So this successor pose is given as xt. This can be also called a successor pose. So this can be estimated as x prime, y prime, and theta prime. And this control action ut is determined on various factors. Ut can be determined based on the waypoint trajectory. Let's suppose a waypoint, predefined waypoint for a robot is given, or the occupancy grid map, that is also you can say to navigate in the free space. So there are many things which can determine the UT, but the one of the basic we will see, like let's suppose a pure pursuit algorithm is there. In that robot follows the waypoint. So again, we'll take one example. So this is our map axis, and let's suppose our robot is here, and this is the position at t minus 1. So xt minus 1 is given as, in the previous example, is given as, let's suppose xy, and let's suppose the robot have this goal position, the immediate goal position, like in the next time stamp, robot have to move here, and this have the value we can take as, to not confuse, we should not take x prime because that is the, let's suppose xw, yw, like the waypoints of x and y. So now what will happen? The robot have some heading with the map axis. Here you can see in this direction, the robot is in this direction. So what is the heading here? Let's suppose this is the map axis. So this theta is the yaw angle. So theta is equal to yaw, that is also the heading of robot. Let's suppose that is in this case is 30 degree, because we take positive in anti-clockwise direction. Like this, whatever I'm teaching now, that can be useful in the autonomous navigation of robot or vehicle, anti-clockwise direction. So now what we can calculate, this is our xw, yw, like next point to follow in the waypoint. For clear illustration, we will take little deviation. Let's suppose this is our xw, yw. So now the robot have to move in this direction. Okay. So for moving in this direction, first of all, take yaw as a gamma, and this is the theta. Theta is like the uh, bearing bearing angle which robots should take to reach to the next waypoint. So here theta will be, as you can see from the figure, this divided by this, like tan inverse y by x. So our theta, that is bearing difference, or you can say bearing angle, as a one of the parameter in the pure pursuit algorithm. So this theta will be tan inverse of this quantity. This quantity will be, this is in y axis. So yw minus y divided by this quantity. So this will be, this quantity is xw minus x. Now this is bearing angle. Now already the robot have a heading gamma. So how much robot have to turn now with respect to map axis? So, so bearing difference is equal to, the required angle is theta and the heading of robot is gamma. So this is theta minus gamma. So this is like required angle minus heading. So this we can take as the alpha. And now we can use any of the path tracking algorithm, like PPC, pure pursuit control, or MPC, model predictive control. And you substitute the value of alpha and get the steering output. This is a function of, steering output is a function of alpha. Okay. So you can see the formula. The formula is different for PPC and MPC. So like that, you can calculate how much steering rotation is required to move to the next position. And you have to keep some velocity also. Like if you rotate the steering, but you will not able to reach to the next waypoint unless you have a some velocity. So that velocity also you can determine based on the how far the obstacle is. Okay. So this is one of the basic principle for autonomous navigation. So we'll solve some of the question and also we'll see some other concepts related to the autonomous navigation. So these questions are mostly theoretical in this week. So the first question is asking, the velocity motion model assumes that the noise is a Gaussian distribution of zero mean and some variance. So asking whether this statement is true or false. This statement is false because in velocity motion model, it need not to be Gaussian. The state estimation, like the noise can be modeled by any another appropriate distribution. It should not be always Gaussian. So like triangular distribution can also be used. So this statement is a false. So noise can be modeled by any other distribution. Move on to the second question. The odometry motion model can be used for state estimation, but not for state prediction. So in this question, it is asking like the odometry motion model can be used for state estimation, but not for state prediction. So in this question, as we know, like in the odometry motion model, the state prediction can be done. So this option here it will be the answer will be true here. Like I will go some of the basic things of odometry motion model, then we can understand it more easily. Like first of all, the odometry data is obtained by like some of the motion sensors from the robot. Uh, we can also obtain from some of the sensors like LiDAR and all by matching the previous frame of the data. Okay. And after we know the odometry measurements, like this can be the angular velocity or linear acceleration, we can predict like where will be the robot in the next time step. So the odometry model uses the relative information of the robot's internal odometry. Let's suppose in time interval t minus 1, the robot has a force x bar, y bar, theta bar. 2 at time stamp t, it is going to x bar prime, y bar prime, theta bar prime. So this is just the odometry measurement. So this is the odometry measurement that at t minus 1, the robot position and orientation was x bar, y bar, theta bar. And after at measured at t bar, it was x bar prime, y bar prime, and theta bar prime. So in this, like the algorithm, which is that odometry motion model, we have to compute the probability such that robot is in xt given the action model ut and the previous position and orientation of the robot xt minus 1. And also, like when we have a odometry measurement, so the changes from like the relative difference between xt bar and xt minus 1 bar is a good estimator for the difference of the true pose. Okay, so using this we can estimate, can be used to estimate the true poses of the robot estimate the difference of the true poses of the robot. So what is true poses? That is xt minus 1 and xt. Like whatever is the difference which is measured using the odometry, the same difference can be used to estimate the true pose difference xt minus 1 and xt. So in this question, the option is true. So now we'll see the third question. So the third question is feature-based maps are more useful for localization, and the reason is features can be used for identifying the position of the robot in the environment. So here both statements are true. Like let's suppose we have a 3D map of an environment. Okay. So this is our map origin X, Y, and Z is the out of the plane. So this is our map origin. Feature means some of the landmark. Let's suppose we have a 10 cones as a feature in the map. So this is cone 1, cone 2, cone 3, cone 4. Let's suppose we have 5 cones. Okay. And this is our vehicle moving. So when it is moving, let's suppose the sensor is attached here. Let's suppose a sensor is attached here, which gives the data in the 180-degree field of view. Let's suppose this is a LiDAR sensor. gives the point cloud data with 180-degree field of view. So when the robot is here, let's suppose this is the data here. So in this you can see if the robot detect, let's suppose, five cones here, because all the cones are lying inside the data range. Okay, so I will erase this to make it a little simple. So here the five cones will be detected. So robot can estimate its position, that all the five cones are detected. This means robot is behind the cone one. So it can estimate the position. Let's suppose after some time robot is here. And let's suppose there is a gap of 1 meter between each cone. Now our vehicle is here. So it can detect 1, 2, and 3 cone in 180-degree field of view. The second cone will not come. So we can easily say we are in between second and third cone. In between second and third cone. So here cone is the features. So the robot position lie in between 2 to 3 meter. Okay. Let's suppose we have taken a single 1D dimension of the motion of this robot. So here the first statement says the feature-based maps are more useful for localization. Yes, if features are there, then it is like it will help more in the localization purpose. And features can be used for identifying the position of the robot in the environment. So yes, this statement is also correct, because here we have seen in an example how a cone helps to identify the position of the robot in the environment. Okay, so both statement is true, and the reason is correctly explained for the assertion. So the correct option is option A. Also, like nowadays, HD maps are coming. So what are the features of HD maps? HD maps have features like lane marking. So using the lane marking, the autonomous car keep themselves inside the correct lane. Road sign. Using the road sign, the autonomous vehicle accordingly drive on the road. And then the traffic sign. So these are the features in the HD maps. Okay. And each position is represented using the having the GPS coordinate. So using this GPS coordinates, vehicle localized using GPS coordinates. There are many features of HD maps. Like these are the high level maps which are used by autonomous vehicles nowadays, like Teslas and all are using in USA. So there are many HD maps provided. Like many companies working to create a HD map using LiDAR, camera, radar, and other sensors, even GPS sensors they are using. This was all about the map feature and localization. I guess my network is little poor. Just give me a second. Setting Ethernet connection. Just give me 2 minutes because the system in which I am recording the video now it's connected. We'll see the next question. So, which of the following are true about the occupancy grid estimation algorithm? So, we'll see each statement. So, it is asking which of the following are the true about the occupancy grid estimation algorithm. So, the first option is the algorithm is similar to the binary Bayes filter with a static state. Yes, this option is correct. The second is the occupancy of each cell is estimated independently. Yes, the occupancy of each cell is not depending on the other cell. It is estimated independently. So option B and A is correct. C is the algorithm use an inverse motion model. No, this option is wrong. The algorithm uses an inverse measurement model. Yes, this is correct. The algorithm needs only the measurement information at each step. So this is wrong. Also, we will see one of the applications of occupancy grade. Basically, what happened, I will again give an example of autonomous vehicle. This is our autonomous vehicle, and this is the road area, and this is, let's suppose, a lane. Okay, so our vehicle is moving, and it have a lidar sensor here. You can take any sensor, like most of the common uses are lidar, radar, and camera. So it will lidar will give a 3D data, point cloud data of the environment. So the data estimated by lidar is all this. Actually, it will give the complete 3D 360-degree field of view. So this is, let's suppose, lidar data. And we have some obstacle in the path. Let's suppose there are some trees. There are some other cars going on. Okay. And our vehicle is moving in the forward direction. So what happened in this? So after collecting the data from the sensors like LiDAR, it will create the environment in the grid. Let's suppose we have detected the road area because we are not interested in navigating outside the road area. So this is the road area detected by sensor. Now we have divided this into the small grid. Now if we have to navigate, let's suppose our predetermined path was, let's take a obstacle here also. Let's suppose our predetermined path was like this. Okay, with the green. I think green is very light. So I will take some other color. Let's suppose the predetermined path was like this for this vehicle. So now after detecting obstacle, it will search which grid is free. So these grids are the free grids. So the vehicle will take the position like this. Okay. So here the occupancy grid mapping helps a lot while avoiding the obstacle. So the application of this occupancy grid estimation algorithm is to avoid an obstacle while navigating. So now coming to the fifth question. So in general, in the measurement model, it is reasonable to assume that probability of each measurement value is independent given the current state xt. Probability of zt such that xt is given is the product of probability of zt k such that xt is given k is from 1 to k. Knowledge of the map is redundant in estimating the joint probability of measurement values. So both the statements are false here. So like when the map and the current state should be known. So the like it is given as probability of zt such that xt comma map. Map is also given k is equal to 1 to k probability of ztk such that xt comma map is given. So like both the map and current state should be known to the and for the probability of measurement values can be considered independent. So both the statements are false here in this case. Okay. So the map is not given here. So the knowledge of the map should be there. It is dependent on this. Okay. Because the following density function is not used for modeling the noise in the range finder model. So this Gaussian, exponential, uniform, these three are used. Poisson is not used. So the correct option is Poisson. So we have already seen this question. This is having the answer as a Poisson. We'll solve one question on the Kalman filter in today's lecture because the Kalman filter is one of the important things. So we'll see the formula like the Kalman filter algorithm. Like this question is from the last week. So first we will see Kalman filter algorithm. Here only we'll write. So that depend on mu t minus 1, covariance t minus 1, ut measurement zt. Mu t bar is equal to, so this is just the algorithm which we have studied in the last lecture. You can see this equation there. Kalman gain kt is equal to So in this question it is given, assume the following dynamics for a one-dimensional parameter xt is equal to xt minus 1 plus ut plus e, zt is equal to xt plus eta. Both epsilon and eta are zero mean Gaussian random variables with zero point 0.1 variance and zero mean. Given that initial belief is Gaussian with zero mean and unit variance, u1 is plus 0.1, z1 is plus 0.11. Which of the following closest to the new belief state after a Kalman filter update? So in this question, it is given both eta and epsilon are zero mean Gaussian, random variable with 0.1 variance. Huh. The initial belief is Gaussian with zero mean. So this mu t minus 1 is 0 and unit variance. So sigma t minus 1 will be 1. Okay. Ut is given as 0.1 and z1 is given as 0.11. So our Kalman filter algorithm can be written like this: 0, comma 1, comma 0.1, comma 0.11. Because from here mu t minus 1 is equal to 0, sigma t minus 1 is equal to 1, ut is given as 0.1 and that is u1. Here we can write directly u0 is 0, sigma 0 is 1, u1 is 0.1 and z1 is given as 0.11. Okay. So now we'll substitute all this value. So at is 1 from this equation because you see the coefficient of xt minus 1 is a is equal to 1 here, b is also is equal to 1 and c is equal to 1 here and z is also equal to 1 here. Sorry, d. So from this ABC we will take as 1. So our mu t bar is equal to 1 into, first let's break down, ut minus 1 plus ut. Sigma t bar is equal to sigma t minus 1. At transpose will also become 1 plus rt. Kalman gain kt is equal to sigma t bar ct. C is also 1, so this term we can remove, plus qt inverse mu t is equal to mu t bar plus kt into zt and c is 1, so only mu t bar and covariance is I minus ct is 1, so I minus kt into sigma bar t. So now we'll substitute all the values. So for u1 bar, it will be u0 plus, this is actually u, this is not mu, this is u1. So this will be 0 plus 0.1, that is equal to 0.1. Now that is sigma t minus 1 plus rt. So 1 and here you can see the RT, here the variance is 0.1 for the noise. So this is equal to 0.1. So this value is 1.1. Now our KT is equal to sigma T bar, that is 1.1 into 1.1 plus 0.1 inverse. So this will be 1.1 by 1.2, 11 by 12, 0.917. Again, The belief in the timestamp t is given as mu t bar, that is 0.1, plus Kalman gain is 0.917 into ZT is 0.11 minus mu t bar, that is calculated as 0.1. So this is equal to 0.1 plus 0.917 into 0.01. So this is equal to 0.10917. The last one will be I is 1 minus KT, we have calculated 0.917, and sigma bar T is 1.1. So this will be 0.083 into 1.1. When you calculate, you will get 0.0913. So this will return, Kalman filter algorithm return mu t, comma, covariance at time instant t. So this is equal to 0.10917, comma, 0.0913. So this question was based on the last week. So today we will stop the lecture here only, and this video will be uploaded on YouTube also. Yeah, Ram Kumar, you have raised your hand. Any question? She is not audible. Just give me 1 minute. Now can you speak? Sir, am I audible? Now audible. Sir, in that question in previous week, the answer is given last option, sir. Last please, sir. Which one? The same question that we discussed now, Kalman Filter. Sir, mean is given 0.1 and variance is 0.1. No, the correct option will be mean is 0.1 and the variance is 0.09. Yeah, 0.09 can be, they have taken as 0.09 as maybe 0.1. Sure, sir, sir. Okay, sir. But the exact answer when you calculate, you will get 0.0913. Sir, uh, can we the 80 calculation, sir? 80 how we sir. So KT we have calculated. See, the formula for KT was here. Sigma T covariance T bar into CTT. So CT is 1 here. So this term is reduced. So this became KT is equal to CT is 1. CT transpose will be also 1 plus QT inverse. And QT is the covariance of the noise. So here it is given both epsilon and eta, both the noise are zero mean with Gaussian random variables with zero point 0.1 variance. So here we have taken 0.1 and this value we have calculated in step 2, that is 1.1. So this will be inverse of KT is equal to 1.1 into 1.1 plus 0.1 inverse. So this will be 1.1 by 1.2. For example, 2 or then what will be relative city transpose, sir? Like here it is given one dimensional system. It won't be given as like if it is if it is one dimensional and the value is 2, then the transpose will obviously be 2. Like transpose of one dimensional matrix is the same. But when it is multi-dimensional, then you have to take the transpose of that. Okay, sir. In all the sessions, we discussed only one dimension. Yeah. Let's suppose here xt is equal to 5, xt minus 1. Then here a is equal to 5. So matrix A is 1 cross 1. And let's suppose C is here given as 2, like 2xt. Z is T is equal to 2xt. So C is equal to 2. So C transpose will also be equal to 2. In one dimensional, both are transpose and the same matrix are equal. But in multi-dimensional, you have to take the transpose and then you have to multiply. Sir, this is same assignment in both question number 3.
Uh, the answer is extended Kalman filter and practical filter is clear, sir. Can you tell me why Kalman filter is not correct, sir, in that assignment?
Last assignment.
This is the last assignment question number 3, sir. Change the yes, sir.
So when the robot is moving in circular motion, then the direction is changing. The Kalman filter is for linear motion only, linear trajectory only. So here the trajectory is non-linear. That's why it can be estimated using extended Kalman filter.
Sure. So in Kalman filter, we only
Linear. Yeah, yeah.
okay, sir. So, uh, this correctly is sir. The only difference between carbon filter and extended carbon filter is non-linear or same.
Yeah, we can deal with non-linear model also in the extended Kalman filter.
Okay, sir. Okay, sir. That's it. That's it.
Okay, welcome. So thank you everyone for attending today's lecture. So this video will be uploaded. You can watch if you missed this lecture series. Thank you.
Sir, if previous also is possible, please update, sir. Since now,
Oh, okay. Sorry, I missed to upload the last week video. Okay, I will upload it today, both the week.
okay, sir. Thank you.
Okay. Well.